Section 4.7, optimization problems. In this section, we're going to look at some application problems that we can make use of our derivatives to locate maximum and minimum values of a given quantity or requested quantity. All right, so it's just kind of putting into use everything we talked about in terms of using the first derivative primarily, which is what we did. I'm also going to remind you of how you can use the second derivative to determine where a function has an optimal value, right? Whether it be a maximum or a minimum. Right, so in this case, we call these optimization problems because we are looking for the absolute maximum or absolute minimum value of a given function in the context of the application in which it is presented. Now, these all follow a pretty standard procedure in terms of how we address these types of application problems. So there is a step-by-step process. Of course, the only thing that then will change is the specific function or equation that you have to work with, depending upon the application or the quantities involved within those applications. All right, but they're all going to follow the same basic process. So here's what we do. First of all, as you would of course do with any application problem, we have to make sure we understand the problem. So read through it a couple times, make sure you get the general gist of it. What exactly is the problem talking about? What are the quantities involved? That type of thing. I always recommend drawing a diagram whenever possible, and you will find that a lot of these, not necessarily all of them, but a lot of them will require some type of geometric shape, or refer at least to some geometric shape. And I always find diagrams helpful to help organize. You draw your diagram, label the parts of the diagram. It helps to visualize the relationship between the quantities that are presented, and of course keeping track of all the different quantities that we're dealing with. Step 3, don't overlook this step. This is, I consider this probably one of the more critical steps that I think gets overlooked or taken for granted. Introduce your notation. All right, you want to define your variables because you're going to be dealing with multiple unknowns in these particular problems. So labeling your variables, labeling the quantities, clearly, so that you can keep track of them. Now, don't take that for granted. So, if you want to use X and Y all the time and or whatever quantity or variable you care to use, you're free to do that, as always. But just make sure you're clear as far as what each variable represents. That way, when you come to that point that you're actually going to answer your question, you know which quantity or which value you're referring to. Now, we're going to assign a symbol to represent the quantity that is to be optimized, whether we're finding a maximum or minimum value. If we have a specific variable in mind or a symbol in mind, then we can use that. So for example, if I'm trying to say, in one of our examples, we'll be maximizing the area of a region. So of course I'll call that A, right? A for area. If you don't particularly have a specific symbol in mind or variable in mind, by default the generic labeling is we use the letter Q for quantity, right? So you'll see in different examples or problems where they use this Q value to label the quantity that is being optimized. But as with any other type of labeling of unknowns, you can use whatever you want. Again, just be clear as far as what it is you're labeling or representing, so that we can keep all of our information straight. So that's all about, those first few steps are all about just understanding the information. All right, so I label all of my unknowns, my variables. Step 4 down at the bottom. We then want to express Q in terms of the other variables involved. So that quantity that I'm trying to optimize, what am I trying to find the maximum or minimum value of? I need to come up with an equation or make use of a pre-existing formula, if there is one, in terms of the other unknown quantities involved. So for example, if I'm, like I said, the one I referenced earlier, if we're trying to say find the area of a rectangle, we have a formula for that, right? If the area is length times width, so we start there and just use our formula, and then plug in our variables representing the length and the width. Now, since we are ultimately going to be finding the maximum or minimum value of that Q, that quantity, then we're going to be making use of our derivatives. So we are going to need to differentiate our quantity equation, right? Area or what have you. So in order to do that, we need that equation written in terms of a single variable. Right? So if I have the area for a rectangle, area equals length times width, and I want to differentiate that function, I need it strictly in terms of either the length or the width. Right? So what we're going to have to do then is sub out one of those variables using some other relationship that exists between those unknown quantities. In other words, do I have a relationship between the length and the width, an equation that I can utilize that would allow me to substitute out either L or W in that area formula, the area quantity that we're trying to optimize. But again, I'll show you how all this works. So I'm looking for some other relationship between those quantities. Now, of course, the problem here, and this is the issue I always find, I guess the biggest mistake with these problems, you've got to keep your equation straight. In other words, there's one equation, one quantity that I'm trying to optimize. So that's the one that I want to work with. I then have to discover another equation that relates my unknown variables so that I can sub out or rewrite that quantity to be maximized or minimized in terms of a single variable. So you got to keep straight which equation you're working with. And then lastly, once you have that quantity written in terms of a single variable, then there we're pretty much back to business. We'll use that equation, we'll find our critical numbers, go through the process that we use for finding absolute maximum or absolute minimum. Now, in the examples or in all the problems that we worked previously, when we were finding maximum and minimum values, we made use of that first derivative test. So remember our first derivative test, and this is in terms of an absolute instead of just relative, but the first derivative test for absolute extreme values, if we have a critical number c, so suppose that c is a critical number of a continuous function f, defined on some interval, right? And whatever, in this case, we're looking at whatever the domain of our function happens to be. We'll talk a little more about that as we go through. If f prime is positive, right, greater than 0, for all x less than c, so if f prime is positive, that means what? Our function is increasing. And f prime is negative for all values of x greater than c, so then we go to decreasing. So there we got an increasing function changing to a decreasing function. Then we know that f of c is the absolute maximum value, right? So c, our critical number, is the location of an absolute max because we're going from increasing to decreasing. Now, what you'll see in these particular problems, we're going to find critical numbers, right, as we've done before with our first derivative. We're only going to come across one critical number. And so checking if you want to use first derivative test to see if we're positive or negative on either side of that critical number, right, there's only going to be one that we're going to deal with, so it makes it a little more straightforward. And then conversely, if f prime is negative, right, so our function is decreasing for all values of x less than c, and then f prime is positive, so our function is increasing for all values of x greater than c. So if we go from decreasing to increasing, then we have f of c as an absolute minimum, because again, it's going to be our only critical number. Now, in general, if you do have multiple critical numbers, then that's where we would have to go through that closed interval test, right? And we would have to check the value at each of those critical numbers if we have multiple locations where we have, say, relative maximums. But that's not going to be an issue with these. They're all going to be single critical number type problems, or at least relevant critical numbers. And then we can use this first derivative test or directly to find absolute max, absolute min. Now, what I'm going to do instead in these particular problems, so there's our first derivative test. So you can make use of that if you wish. Remember, there is also a second derivative test. The second derivative test for, oh, I know why it's doing that. The second derivative test for critical numbers, or for not critical numbers, but absolute max and min. I just forgot to label this. I wanted to put a label on it. So second derivative test. Now, what the second derivative test did was it made use of the second derivative, and that, remember the second derivative we used to check for concavity? If the second derivative is positive, it means that our function is our graph of our function is concave up. And if the second derivative is negative, then it means the graph of our function is concave down. And we didn't use second derivative test previously to find maxes and mins because we were just making use of our first derivative, which we needed to find anyway. But in these examples, I'm going to use second derivative tests just because when you look in the solutions manual for these problems, they use second derivative tests. So I don't want to confuse you any more than we need to. So I'm going to just remind you about second derivative tests, but you could just as easily use first derivative tests just like we used before. Okay. But also, since we're only going to be coming across a single critical number in these cases, it's almost not even necessary to test it. So it's going to fit either max or min, whichever the situation is dealing with. But we do want to, of course, make sure. We want to double check and make sure that we do actually have the absolute max or min value of the function. So we're going to at least mention these on a test. If you don't necessarily do this, I'm not going to dock you for it. I mean, find your critical number, find your values, great. You don't have to prove to me that it's an absolute max or min. But I am going to mention this because when you do check these, that this is what they do. So reminding you of second derivative test, because again, that's what I'm going to use here. So if f double prime is positive, all right, for all values of x, then f has an absolute minimum value at that c value. Right, so if over the entire domain of our function, and you'll see what I'm talking about when I do the examples. So normally we'd say across an interval, right, or at our critical numbers, I should say. But in this case, if f double prime, if our second derivative is positive for all x, then f has an absolute min, because remember, second derivative being positive means our graph is concave up, right? It looks something like this. And so we have an absolute minimum value at that c value or at that x value. And then conversely, right, if f double prime, our second derivative, is negative for all values of x, I guess I could call these c values. I don't have to call them x values. So if f double prime of c is negative for all values of c, then that would mean our function's graph is concave down, which would mean that our function has an absolute max at that value, right? So first, as always, we find our critical numbers. We'll use our first derivative to do that. But then once we find those critical numbers, we can determine whether there's an absolute max or absolute min by checking the second derivative. So it's reminding you how to use that. That's what I did in these examples. But again, you can use first derivative test as well. All right. But again, I don't want to make that the bigger issue. For me, it's more about making sure we actually find those critical numbers. All right, so for example, and this first one is just a little generic example, nothing specific here other than we're just finding some values. So for example, it says find two numbers whose difference is 100 and whose product is a minimum. All right, so as soon as I see that maximum or minimum question, then I know I'm looking at optimizing a function. Right? So when you put this in the context of other types of applications that we've looked at, as soon as you have that request for a maximum or minimum, this is an optimization problem, puts us into that mindset. So what is it that we are maximizing or minimizing? We are minimizing, in this case, the product of these two numbers. So that's the quantity that we're interested in. Now, other unknowns, of course, are the two numbers themselves. So I just labeled them as x and y. So I said, let's let x be the first number, y be the second number. Again, you call them whatever you want. I mean, those are just simply variables. Call them a and b, call them m and n, whatever you want. That's purely arbitrary. Just make sure you keep track of everything. Now, the quantity that we are interested in is this guy. We're interested in that product. All right, we want the product to be as small as possible. So there's our equation for our optimization quantity, our minimum product. Q would be equal to x times y, the product of our two numbers. But then we said we need to express that in terms of a single variable so that I can then make use of our derivative, right, to find our critical numbers. Now I called it Q. Again here, if you want to call it P, you can call it P for product. Now I need some other relationship between my two variables, between my two numbers, x and y, so that we can use that equation to sub out one of those variables. And the other information that we have in the problem is that the difference of our two numbers is 100. So that gives me this relationship that the difference between x and y, x minus y, is 100. I can then take that equation, solve it for one of those variables. It doesn't matter which one, you pick whichever, so that I can sub one of those variables out of our Q equation, because that's the one I'm interested in. Ultimately, that's the one I want to minimize. So in this case, what I did was I solved for y, and I have y equals x minus 100. I get an equal sign there. But again, you could just as easily solve that for x. It doesn't matter which one, I just need to sub out one of those variables in my product formula. So I have y equals x minus 100, so I went ahead and subbed in place of y, x minus 100. And so x times y is now x times x minus 100. So that's getting our quantity written in terms of a single variable. Now from here, it's business as usual in terms of finding the critical numbers and then determining whether it is a maximum or the location of a maximum or minimum value. So since I want to differentiate this function, so I have q equals x times x minus 100. Went ahead and distributed. I've got q equals x squared minus 100x. Find our first derivative, q prime, which would be 2x minus 100. And again, that's whatever is needed in order to differentiate the given function. We want our critical numbers. So finding our critical numbers, we set the function equal to 0, or we look to see if there is any value at which the function is undefined. Right, so remember our critical numbers. So no issues with undefined in this case, so it's simply a nice little polynomial, set that equal to 0. I get 2 times x minus 50 equals 0. I get x minus 50 equals 0, or x equals 50. Now again, notice I only have one critical number. So if you want to double check to see if that is actually the location of a minimum, then again, you could use that first derivative and you plug in values, remember, on either side of 50 into that first derivative. Remember we did those little test strips. Or you come over here as I did to the right and say, well, let's look at f double prime. If this is f prime, q prime is 2x minus 100, then q double prime, our second derivative, is just 2, right? I called it f over here. I guess I should call it q double prime. And since our second derivative is equal to 2, that means that's a constant. It's a positive number. And it's positive always, right? I mean, it's 2. It's always going to be positive. And since the second derivative is positive for all values of x, then that means the graph of that function is concave up over its entire domain. And of course, if you look at the function, I mean, q is a quadratic, ultimately, right? Q is x squared minus 100x. It's a quadratic function. We know the graph of that is a parabola, right? So it makes sense that there would be an absolute minimum value. And we just found it to be at x equals 50, right? And so that is because the graph of the function is concave up over its entire domain because the second derivative is equal to a positive constant, right? But again, that's, verification purposes. I'm not going to hold you to that necessarily on a test, but this will be done for each of the problems that we look at. Now, of course, we're asked for two numbers, so once I find the x, then I can go back up here and plug it into that equation that we have for y. We know that y equals x minus 100, so I just back substituted. I plugged 50 in there. 50 minus 100 is negative 50, and we have our y value. So I'm looking at those as our two numbers, x equals 50, and y equals negative 50. The difference between those two is 100, and this is telling us also that the product of those two would be the smallest possible product for two numbers whose difference is 100. That's how optimization problems work, okay? So a few other examples. I think I have 3 more, and these are applications. So full-blown applications give you a good idea with these. Now, I find for the most part that these tend to go pretty well. Like I told you earlier, the biggest issue is always in just making sure we keep the equations straight. Right? What is the quantity? What is the equation? What is the function that I'm optimizing, that I'm finding the maximum or minimum value for? And then I have a second equation that I have to use to relate the unknown variables so that I can express that quantity in terms of a single variable. Right? So you just got to keep those two straight. Otherwise, like I said, once you come up with your equation in one variable for your optimization quantity, then you're back to just finding critical numbers from there. So then, of course, you do have to differentiate and all that, but these tend to go pretty well, I think, for the most part. All right, so the next one. Here we're asked to find the dimensions of a rectangle with an area of 1,000 square meters whose perimeter is as small as possible. All right, so we're told that the area of our rectangle is 1,000 square meters. We are interested in minimizing the perimeter, right? We want to find the rectangle whose perimeter is as small as possible, right? So always identify what is the quantity that we are minimizing or maximizing. So we do have an equation, an already established formula for the perimeter of a rectangle, right? So I'm trying to make the perimeter as small as possible. What's the perimeter of a rectangle? Perimeter is 2 times the length plus 2 times the width. So again, that's the quantity that we're trying to minimize. It contains 2 variables, L and W. We need to get rid of one of them. So we need to sub out either L or W. Well, we have to look for some other relationship between those 2 quantities. We have another relationship right above it. We're told that the area is 1,000 square meters. And again, this is a rectangle, so we have a formula for that. The area is length times width for a rectangle. We know the area is 1,000 square meters, so I have an equation, 1,000 equals L times W. So that's a second equation that I'm using to relate our 2 variables, our 2 unknown quantities, length and width. We then want to solve that equation for one of those variables. And again, here it really doesn't matter which one. Pick one, doesn't matter. I chose L, so solving for L, and I've got L equals 1,000 over W. And then we're going to substitute L, or in place of L, in our perimeter formula, right? So now I'm back to the quantity that I'm optimizing, in this case perimeter. So I went ahead and subbed out L with 1,000 over W. So I've got 2L, or now 1,000 divided by W, plus 2W. I now have our perimeter in terms of a single variable, in terms of W. And so from this point forward, again, we're just now back to finding critical numbers. I want the critical values of P. We'll use our first derivative to find them. And then we'll determine whether that is the location of a maximum or minimum, which, again, it should be a minimum because we are looking at the smallest possible perimeter. Now, the rest of this is going to be all about rewriting, so we know we want to differentiate this thing. So first I just multiplied 2 times 1,000 over W, so I've got 2,000 over W plus 2W. And then I just rewrote that as 2,000 times W to the negative 1 plus 2W, because again, we know we're going to differentiate this thing. So I'm going to go ahead and put it in terms of a power function. So then our derivatives, so power rule, negative 2,000 W to the negative 2, here's P prime. Derivative of 2W would be 2. Now again, I'm just differentiating with respect to W. Right, that's the reason for putting this in terms of a single variable. And then we look at where that derivative is either equal to 0 or possibly where it is undefined. Now notice that this function is undefined. I mean, if I were to write that as 2,000 over W squared, right, this derivative would be undefined for W equals 0. So I mean, W equals 0 is also a critical value. But think about what that would mean. Remember, what is W? W is the width of our rectangle, right? And W can't equal 0. W is going to have to be a positive value. So this is where I kind of mentioned earlier, if you come across multiple critical numbers there's only one that's going to be relevant to the application. All right, so in this case, w equal to 0, even though it is a critical number of our function, of that perimeter, of that perimeter function, it's not applicable to this application because the width of our rectangle has to be positive, right? So yes, it's a critical number technically, but it's not relevant to our application. So I went ahead and set then this function equal to 0. So I've got the negative 200w to the negative 2, or plus 2 equals 0. So I then went ahead and solved that for w. So the first thing I did was just subtract 2. I went this route. You know, it's all about solving the equation or whatever is necessary to do that. So then I went ahead and divided by w to the negative 2. Went ahead and divided by negative 1 as well. Divide by negative 2, or we could do it either way. Divide by negative 2. And I've got 1,000 equals w squared. I skipped a little bit of a step in there. Let me go ahead and include that. I don't want to confuse you. So if I divide by negative 2, then I've got 1,000 equals 1 over w to the negative 2. All right, which is w squared. And again, whatever steps you want to follow to solve the equation. I'm just solving that thing for w, so however you want to go about doing that. Regardless, I've got w equals 1,000, w squared equals 1,000. So then w would, now again, technically it's plus or minus the square root, right? We're using that square root property, taking the square root of both sides, so w is plus or minus the square root of 1,000. But again, for the same thing that we mentioned earlier with respect to 0, negative square root of 1,000 would not be relevant to this application because our w, our width, has to be a positive value. So there's our really only relevant critical number. W is equal to the square root of 1,000 meters. All right. Now again, you can check your second derivative if you find the second derivative. Our first derivative was 2,000 w to the negative 2 plus 2. So our second derivative would be negative 2 times negative 2,000, so positive 4,000 w to the negative 3. Derivative of 2 is 0. And if you plug in square root of 1,000, so that would be 4,000 over w cubed. So 4,000 over square root of 1,000 cubed. Now that's going to be a positive value, right? And really it would be a positive value for any relevant value of w that you plug in, right? Because again, w has to be positive. But we do get a positive second derivative at square root of 1,000. And again, since that's the only relevant critical number, then over the relevant interval, which would be positive values for w, we know that this function's graph is concave up, which means that there has to be a minimum at that value for w. All right. But again, my main concern is finding the value. So w is square root of 1,000. That's the width of our rectangle. We can then come back up here and substitute in place of w. So I'd have L equals 1,000 over the square root of 1,000. Rationalize the denominator if you multiply by square root of 1,000 eventually. That would simplify to square root of 1,000 meters, again, is our unit. And approximation, I left them as square root of 1,000, but that's approximately 31.6 meters. So again, approximations here probably makes a little more sense since we're in an application problem. So I would be looking at the dimensions of this rectangle. Actually, it ends up being a square because notice I got square root of 1,000 for each of our width and length. So approximately 31.6 meters for the width and for the length. All right, so to minimize the perimeter of this rectangle, it actually becomes a square. Next, for this one we've got a farmer that has 2,400 feet of fencing, and it wants to fence off a rectangular field. So we're dealing with a rectangle that borders a straight river. It needs no fence along the river, so we're only fencing 3 sides of our rectangle. What are the dimensions of the field that has the largest area? Okay. So we're fencing off a rectangular field, but we're only fencing it on 3 sides because the first side is a river. And in this case, we are looking to maximize the area, right? We want the largest possible area. So there is our quantity to be optimized, the area of this rectangle, which would be length times width. Now notice my diagram. I only labeled, or only would indicate these 3 sides of our rectangle, right? Because the river is on the 4 sides. I don't need any fence there, right? So we're maximizing area. So there's our formula for area of a rectangle, length times width, as I have it labeled. We need this in terms of a single variable. So we look for another relationship between the 2 variables, L and W. In this case, I'm not going to call it perimeter because it's not exactly perimeter. It's only the 3 sides, all right? So if I add the length of those 3 sides, which would be 2L plus W, we know that the farmer has 2,400 feet of fencing, right? So the 3 sides, the sum of those 3 sides would be 2,400. So there's our relationship between our 2 quantities, our 2 variables, in that 2L plus W equals 2,400. Now again, that's the equation that I'm using so that I can sub out one of my variables in the area function, because that's the one that we are maximizing. Okay, so again, you can solve it for either one of the 2 variables. Solve it for L, solve it for W. In this case, I just solved it for W because it was the easier one to solve for. That's usually what dictates which one you sub out, given a choice. Sometimes it doesn't matter, of course, but in this case, it's a little easier to solve for W. So I have W equals 2,400 minus 2L. So we make our substitution into our area function, the one that we are optimizing. So in place of W, I have 2,400 minus 2L. And now there's our area function in terms of a single variable. We then need to find its critical values, its critical numbers. So we want to differentiate that function. I went ahead and distributed L. I've got 2,400L minus 2L squared. Now again, notice that's a quadratic, right? That's a parabola. In this case, it's a parabola that opens down because our L squared is negative. So that means that this function would have a maximum value at its vertex. All right, so at that critical number that we find, it has to have, or would have to be the absolute max, just because of what I know about the graph of that function. So find our derivative. So A prime, again, this is a nice little quadratic, so nothing too fancy. So 2,400 minus 4L, there's our derivative. Set it equal to 0 to find our critical numbers. I went ahead and factored, pulled out a 4. I'm left with 600 minus L equals 0, so L equals 600. And again, that's our only critical number, so it should be the location of our max or min, which again we know from the graph is a maximum. But we can, just to show you how that second derivative test works again, if you find your second derivative, now remember our first derivative was 2,400 minus 4L, right there. So our second derivative would be negative 4. And again, that's a constant. It's a negative constant in this case, and that's the second derivative for the entire function. So it's always negative. And since our second derivative is always negative, then we know that the graph is concave down over the entire domain of that function. And again, we already knew that, right? We said it was a parabola opening down. So there's the justification, there's the verification based on the second derivative. So that gives me my L, which is our length, which is 600 feet that we found. And then we can back substitute that to find W into our equation. Where did we solve for W? Up here. So I can plug that back into L. I've got 2 times 600 is 1,200. 2,400 minus 1,200 is 1,200 feet. And there's our length and width. That would maximize, in this case, the area of our field that is fenced. One more example. This one a little bit more involved, just simply because there were three unknown quantities in this case. But again, it's going to follow the same standard procedure. So here I've got a box with a square base and an open top, so there's no lid on my box. We know that this box must have a volume of 32,000 cubic centimeters. We want to find the dimensions of the box that minimize the amount of material used to construct the box. I guess I should add to that. So we need to build a box that has the required volume, 32,000 cubic centimeters, but we want to minimize the amount of material that we use to construct the box. So you can kind of look at this maybe from the standpoint of maybe we're trying to minimize cost. Put this in, like I said, these optimization problems, these are the types of problems that business, manufacturing, this stuff gets done on a daily basis in the real world. You're maximizing profit, you're minimizing cost. Think of it in those terms. So in one of your homework problems, you're going to have a problem similar to this, where it's going to be put into that context where we're trying to minimize the cost of the construction of the box. All right. So that's a real world application. This is the kind of stuff that gets done all the time. So we need to come up with a formula that we can use to determine how much material is needed to construct our box. And then if we can figure out the minimum amount of material that we need to use to construct it, then we can minimize our cost. Right. So in this case, we're going to refer to that as area. Right. So the amount of material needed or used to construct our box, basically we need to know what's the area, or call it the surface area, is the formal word that we use there. The area of each side of our box that we need to construct, come up with a formula for that, and then optimize that function. Right? Find our maximum or minimum value, or our critical numbers at which we can find the maximum value. All right, so what do we know? We know that the volume of this box is 32,000 cubic centimeters, so we can call that V. We also have a formula for calculating the volume of a box: length times width times height. Right? Now, the quantity that we're trying to optimize in this case, let me start there. We're trying to minimize the amount of material used, so we're trying to minimize our surface area. So let me go to our diagrams that I have down here. If I want the area of each side of our box, now we've got two different areas to deal with, because we are told, first of all, that the box has a square base. So that means that, if we want to call that, say, length times width, or length and width along the base, and then the box has a height. So the area of the base, those measurements would be the same. So I just called those x. That's our length and width in the diagram above. All right, so that's the area of the base, which would be x squared. Now, the box also has four sides. Now, notice for each of those sides, whether it's the side on the left or the right, since the length and the width are the same, then the area of each of our sides is x times h. Right? So, say for this side, it would be w times h. For this side, it would be L times h, right, for the area of each of those sides. But again, since L and W are the same, that's the advantage here, and actually necessary in our case, to limit the number of variables that we have. So it's just x times h for the left and right sides, and x times h for the front and back sides. So there are four sides to the box. Each has an area of x times h. And that's simply, again, because the area of the base, or the base, is a square, right, whose dimensions are x times x. So that's kind of key to this particular problem. Otherwise, we would have too many variables for us to be able to deal with at this point. All right, so I can come up then with a formula for the surface area of this box. I take the area of the base, I'm jumping down here, plus the area of each of the four sides, and there's four of them. So the area of the base is x squared. Each of the four sides is an area of x times h, so there's four of them. Here's our formula for the surface area, or call it the area of the box. So that's the function that we need to optimize, right? We were trying to find, remember, the minimum amount of material needed or used to construct the box. So we're minimizing surface area. Right, now again, our formula has two variables, right? It has x and it has h. So I need to sub out one of those guys. Right, so I need to use another relationship between x and h so that I can sub out x or h in this surface area formula that I'm trying to minimize. So this is where we can go back to our volume. Right, so we said the volume of a box is length times width times height. Of a rectangular box, at least, anyway. Now, we also know that the volume is 32,000 cubic centimeters. We also have L and W both being equal to X. So I can replace L and W with X, and I've got X squared times H as a formula for the volume of this box. Right? So again, that's just subbing X in place of L and W, because those measurements are the same. So then I'm going to take that equation, solve it for one of my variables, and I chose to go ahead and solve it for h. That was the easier of the two, so I don't have to deal with the square root there. But again, it's your choice. I mean, you could solve it for x if you wish. Divide both sides by h and then take the square root. Now also keep in mind here too, similar to the problem we had earlier, remember that x and h are dimensions of this box. So those by default have to be positive values, so they, and that's typical for application type problems. There are some implied restrictions on the variables, the quantities that they represent. Typically they're restricted to positive values, especially when we're talking about construction of a, in this case, the construction of a box. So we have to have positive values for x and h. So there are implied limitations to those values, as we had before. So again, I could take the square root of both sides. If I solve that for x, it would be a positive square root only, is what I was after there. But I went ahead and solved it for h. Again, doesn't matter which one. So I'm going to go back to our surface area that we had, x squared plus 4xh. Went ahead and subbed out h with 32,000 over x squared. So I now have s equals x squared plus 4x times 32,000 over x squared. And like I said, as soon as you do that, you have your optimization quantity in terms of a single variable. Now you're just back to business as usual. I want to find the critical numbers of that function. So I simplified it. I went ahead and rewrote it. X squared 4 times 32,000 is 128,000. I can divide out one of those x's right here and here, and I'm left with x squared plus 128,000 over x. Now notice again, that is, that's our function. I went ahead and if you rewrite that, I've kind of skipped a couple of steps in here. So I've got x squared plus 128,000, but I think by now you should be able to handle something like this, because I do want to find the derivative of that function, right? Now that I have the function in terms of a single variable, I need my critical number. So I went ahead and rewrote it as a power function. So our derivative then would be 2x power rule minus 128x to the negative 2, or minus 128,000 over x squared. All right. Again, I trust by now that should be pretty straightforward. But there's our second derivative. Now notice that this derivative is, as with the one we had earlier, it is undefined when x equals 0. But like we said, that's not relevant to our particular situation, because x is the length and the width, or represents the length and width of our box. So by default, again, that has to be a positive value. So the fact that I have a critical number of 0 here is irrelevant. Doesn't make sense in the context of the problem. So I went ahead and set it equal to 0. Find whatever other critical number might exist. I went ahead and added the 128,000 over x cubed. So I got 2x equals 128,000 over x cubed. X squared, excuse me. Then I multiplied by x squared to clear the fraction. That gave me x cubed on the left, and then dividing by 2 gives you 64,000 on the right. And in this case, we took the cube root. All right, now cube roots are nicer because they're all, you don't need a plus or minus there. But the cube root of 64 is 4. The cube root of 64,000 is 40. And that gives me the value for x. All right, which again, remember that represents the length and the width. Now, we can verify that there is a, we were looking for what, minimizing the value or the quantity, our surface area. So we could verify that that is the location of a minimum by looking at our second derivative. All right, so with our first derivative of 2x minus 128,000 x to the negative 2, our second derivative, the derivative of 2x is 2. The derivative of 128,000 x to the negative 2 would be positive 128,000 x to the negative 3. Or 128,000 over x cubed. Which, again, because x is always a positive value, then that second derivative would also always be positive. All right. And so again, just for verification purposes, second derivative is positive for all relevant values of x. And so that tells us that the graph is concave up, which means I have a minimum value at our x equal to 40. All right. So again, that's just the justification verification there. But like I said, you're always going to have one critical number for these functions, so whether or not you actually go through this process, I don't care. All right, so we know we have a minimum value at x equals 40 centimeters. We can also then plug that back into our equation at the top to find our h value. So plugging in 40 for x, I've got 32,000 divided by 40 squared, which will give you h equal to 20. And so there's our x that we found, and here's our h that we find by back substitution. Now remember, x represents two of your dimensions. X was the length and the width. So we want the dimensions of the box that will minimize the amount of material. Length and width would both be 40 centimeters, and our height would be 20 centimeters. Okay? So that gives you a few examples of these optimization problems. Like I said, they tend to go pretty well. Just follow the process. Two main parts. First, make sure everything is labeled clearly in terms of your variables. Label your quantity to be optimized. Label the other variables within the context of the application. Secondly, keep your equations straight. What's the quantity being optimized? That's the main function or equation that I want to work with. I have to come up with that second equation so that I can sub out one of the variables in my optimization equation. And then once you do that, you're just back to finding critical numbers from that point forward. And that is it for that section.